Stuck on CNA labs? Tired of scattered tutorials? This full course covers every exam topic with real lab configs. Grab your free lab in the description. Ready to pass CNA and boost your career? Start now!
Hello everyone. In this session, we will learn about the TCP IP protocol suite. After this session, you should understand TCP and UDP, their packet header structures, and their transmission characteristics. Second, you need to master the IP packet, its header structure. First, at each layer. In our previous sessions, we discussed the OSI 7 layer. At each layer, there are corresponding protocols. Some working protocols. The most commonly used ones are the top layer protocols, application layer protocols. But as network engineers, we are actually more concerned with the lower layers, transport, network, and data link, and physical layer protocols. Right. The most important one are the transport and network layers, because for data link and physical layer protocols, we have limited room to operate. Very limited room to operate. Are mostly fixed. We need to master the protocols here. TCP and UDP at the transport layer, and the IP protocol at the network layer. Among application layer protocols, the most common ones were also covered earlier. Right, like HTTP and HTTPS. Right. HTTP uses port 80. HTTPS uses port 443. It is the hypertext transfer protocol. It provides web access. Web access pages. Right. Then there is Telnet, a remote access protocol. A remote login protocol. Port number 23. So the port numbers mentioned here are all TCP port numbers. Are all TCP port numbers. Telnet provides remote management functionality. Right. FTP has 2 port numbers. Also TCP ports 20 and 21. These 2 ports, it's called file transfer protocol, mainly provides file resource sharing on the internet. That is, file upload and download. Then SMTP, simple network TRA, mail transfer protocol. This one is 25. Then POP3. It is Post Office Protocol 3. Actually both provide email services. Port number, SMTP is 25. POP3 is 110. Then TFTP. TFTP this port. I've specifically marked it here. It is a UDP port number. TFTP is a bit like FTP. Right, it's called Trivial File Transfer Protocol. Simpler than FTP, generally speaking. We network engineers actually use this protocol often. For example, if we need to give network devices, switches and routers, right, upload or download their images, upload or download their configuration files, and so on. When doing these we will use TFTP because it's simple to start. A small piece of software can get it running. And there's no overly complex authentication or other strange things. It's just more convenient to use. So we will use actually this thing on the internet. We actually don't recommend because it is too simple. It has too many vulnerabilities. Many security issues are not considered by. These are some common application layer protocols. These application layer protocols must map to our transport layer. You can see that each protocol has a corresponding port number behind it. Right? So it actually corresponds one-to-one with a port number in every application. Every port number in the this protocol must correspond to our port number. There are 2 main protocols in the transport layer. One is TCP, the other is UDP. TCP stands for Transmission Control Protocol. UDP stands for User Datagram Protocol. So what are the characteristics of TCP? TCP's it is connection-oriented. Connection-oriented. That means if you want to use TCP to transmit data, you must first establish a TCP channel. Establish TCP, then you can transmit data. If your channel breaks, if this connection is then your data cannot be transmitted. So we say TCP transmission is reliable. TCP transmission is reliable. And generally speaking, most mainstream applications today basically use TCP port numbers. All using TCP port numbers. Then UDP. It is the user datagram protocol. User datagram, its characteristic is high efficiency. Very high efficiency. It does not need to be connection oriented. It can transmit directly. No need to establish a connection channel. Its transmission method is a best effort delivery. Regardless of whether you can accept it, how big your bandwidth is, it just tries its best to transmit the packet anyway. No matter if you can handle it. Right? Anyway, it just sends. This is called best effort delivery. A characteristic of best effort delivery. Fewer protocols use UDP. Generally, for example, our DNS. The domain name system. This uses UDP. Also, some of our streaming media. Video stream, right? And also voice. Both of these are actually based on multicast. Multicast is based on UDP. Of course, multicast in our daily lives is actually currently the only multicast you might encounter is probably our IPTV. Right? The content played on the TV. This will use UDP. It uses Now, here is a joke. A joke about TCP. Why is there such a joke? Let's take a look. Two people are talking. Right? A says, I want to hear a TCP joke. Right? Then B says, hello? Do you want to hear a TCP joke? A says, I want to hear it. Then B says, okay. I will tell you one. Then A says, I will listen to. Right? Then B says, are you ready? A says, I am ready. Then B says, okay. I am going to send this TCP joke. It is about 10 seconds. Right? Then A said, I am ready to receive your stuff. Right? Then B says, your connection has timed out. Right? After all that fuss, it turns out your connection timed out. And then it starts over again. Do you want to hear a TCP joke? Right? That's the TCP joke. Why does this happen? Because TCP, it is reliable transmission. Every single transmission packet must be acknowledged. Must be acknowledged. So you'll find here. Do you want to hear it? I want to hear. Right? I will tell you. Oh, I will. Right? Then, are you ready? I'm ready. Right? It repeatedly confirms. So this process is very tedious. So we say, it is reliable, but it is not efficient. Right? But if it's UDP, right, then its efficiency is much higher. It just says, I want to hear a UDP joke. And then, hey, it just, bam, sends you one over. Hey, 10 sec, this 20-word joke is sent to you. As for whether you were ready, or if you can even hear it. I don't care. I don't care. Right, this is a characteristic. It is more however, its reliability. This is a feature of both protocols. You need to remember. In TCP. To ensure its reliability. It has various mechanisms. You need to learn and master these. Many interviews and exams often test on this. The first one is the TCP three-way handshake. We say TCP is connection-oriented. It needs to establish this TCP connection first. So how does it establish this TCP connection? In this case, there is an initiator and a responder. Someone has to reach out first. Right, it's like dating. Someone has to confess first. So the initiator here wants to, with our responder, establish a TCP connection. At this time, it sends the first TCP handshake. In this first handshake, there is a SIN. We call this a synchronization here, for example, let's say our synchronization sequence number is 1. The synchronization and then, after I send this packet, after sending the first TCP packet, it enters a state called SIN sent. The SIN packet has been sent. And then, it waits for, right? Waiting for the other to confirm. Then, the response, after receiving this TCP, with SIN equals this TCP packet. It enters, SIN received. The SIN packet has been, and then it starts allocating, here, for example, you want to provide some access to my specific port number. Essentially, you want to access a specific application of mine. Right? So at this time, I'm the corresponding application to prepare some things for you. Like CPU resources, memory resource, right, and so on. All these resources need, here, resource prep, and then, after the preparation is done, it sends out, the responder side sends out a TCP packet as a response. This is the second TCP sent by our responder. When sending, note that there is an ACK here. The ACK here is, pay attention, this too is not random. This too is derived from the initiator's side earlier. The sequence number of the SIN sent over. +1, that's how it's formed. If what you sent was 10, then here on my, the ACK sent, understand. It's the previous SIN sequence number. +1, used for telling the initiator that your TCP packet with SIN equal to 1. After the other side, the packet I sent over. The other side, this is an acknowledgement process. Also in this packet, SY also needs to mark a packet sent by itself. There will be a SI, for example, is an 8, right? This is in the second in the TCP packet sent over in the second step. So it is sent to our initiator. The initiator receives this. Receives the second TCP packet. Right. At this, it enters the established. The connected, enters the and then starts allocating resources. For example, you request a web page. At this point, your memory need to be TCP, these CPU resources and process resource need to be prepared. Right. Because the other side has responded to you. Okay. So SIN is sent to the other side. Right. Sent, then the initiator receives it. After receiving it. So on the initiator side, it doesn't, on my initiator side. This packet I sent. Right? This second packet I sent. Whether the other, the initiator needs to do a final confirmation. A final, taking this S1's. Sequence number 8. Do a confirmation. Here the ACK is right? Increment by 1 from 8 plus 1 is, so an ACK of 9 is sent back. It's sent to the responder. The responder receives this ACK equal to 9. It then knows the S1 packet, the one with sequence, has been received. At this point, it can also enter the established. In this way, the two devices, their connection channel is fully established. The connection is now, once the TCP connection, we can subsequently send our data. We can send data, so this is called the TCP three-way handshake. The TCP three-way, this three-way handshake. During internet communication, on the intermediate links, where stability and security are unknown, using 3 steps to establish a connection is actually the most efficient method. One less or one more step would be unsuitable. If you had one less step, right? If you remove the last step, then it would be considered that the responder wouldn't know if the second packet I sent was received, right? If you had one, it would feel cumbersome. What do I mean by one? For example, the responder here, right, receives this SIN equals 1. I first send an ACK equals 2. Acknowledging your SIN equals 1 packet was received. And then, send my own SIN equals 8. Then the other side replies with an ACK equals 9. Right? In this, it becomes 4 These two middle steps are now separate. Right? Splitting them apart results in a 4-way handshake. This 4-way handshake is a bit wasteful, right? Why not just combine them? Right? Combine them together. In that case, efficiency is high. So, TCP does want to be efficient. It also wants when the intermediate link is unknown to both parties. Using a 3-way handshake is actually the most efficient method. After the connection is established, it's time to transmit data. Right? For data transmission, there is also a mechanism. We call it the sliding window mechanism. Called the sliding window mechanism. What is a sliding window? This window is like the opening for data transmission. right? It slides. Sliding means it can grow larger, just like opening a, right? If the wind is strong, you make the opening smaller. If there is no wind, right? You open the window. This window is a, right? The window is a, we call this the sliding window method. It is mainly used for on busy links. Flow control. Flow control. For example, I send a few packets over. Suppose the window size now is 10 packets, right? And then I send them to the receiver. After receiving these 10 packets, they are placed in in the buffer area, and then my CPU, these processes, or some application protocol will fetch the data in the buffer, fetch the packets, right? And then process them. For example, now reads 3, right? Reads 3. Then in my buffer, there are 7 packets left, right? Right. At this point, at this moment, I need to send an acknowledgement for 3, telling the other side there are currently 3, right? And then, they can send 3 more, and during that I might read another, right? Then I send 3 more, an acknowledgement for, right? Then the other side or on my side, the process is more, right? I read all 10, all 10 are read. Then I acknowledged, 10. Then the other side's, right? This is how we adjust, at every moment. How many packets right, can be handled through, tell the other side. Then what? The other side, and processing sends you a certain, This is called the slide, Okay. So data transfer, I send to you, you send to me. I send, right, finish sending to it, after the transmission, we need to connect, we need to terminate, we need to disconnect, this connection cannot, if it stays connect, this connection will, right, and will also be turned, because it occupies, if the connection resources will be, so this connection, it will be occupied, so it must be released, now, TCP, it requires force, just now for the hand, it requires a 3, right. Now here, we wave goodbye. Just bye-bye. Right. So we need to perform, a student might ask, why does it need 4, pay attention, let's take a look. How these 4 steps are, and why it needs 4, so during the right. After we exchange transmissions. Note. During transmission, there is always a So during this process, we will perform 4, note. During transmission, one side always finishes sending first. It is impossible for both sides to end, right. I send to you, so during this sending, possibly at this moment, I, the initiate, have sent all data completely. At this time, we'll send FIN, finish. Termination message, right. TCP terminate, here there is a sequence number 7. Sent to our responder. At this time, enters FIN, phase 1. Enters FIN. Wait phase 1. Then the responder receives this FIN. After receiving the message with sequence 7. Needs to reply to this FIN content. Right. At this time, ACK equals, your FIN I have received it. At this point, its own side enters close_wait. Which is closing. A state waiting to close. Right. So, then, note. At this time, its content may not have been fully transmitted yet. It still has some or other packets that still need to be sent. Right? So during this process, it keeps sending to, and the other side, right? Until when? Until I, have sent all the data completely. And then, at this point, I, the response, send this FIN packet over. And then the other side acknowledges it. Right? Here it enters the final acknowledgement phase. The other side. Hey. Having received enters the FIN_wait_to state. That is, the process of waiting for the end. Just waiting for its own part has been, right? But it hasn't received, at this point. Right? And then, after it enters the time it all ends after, actually, the and it sends the The ACK is sent, so after the ACK, the final acknowledgement, and this handshake is This is its final, okay. Now let's take a look, our final confirmation now. Is this 4-step I send you a FI, you need to confirm, and then you send me a FI, I need to confirm, That's the process. As for the middle part, why can't the two be, because in between there, data that needs to be, because the volume of, right? Might differ. Might differ. I might be receiving, right? But only need to send a few packets. Right? This is all So in between, there is still data to, right? And then, there is still data so these two steps, if merged, then once one side, the other side is for, right? That won't work. Right? That won't work. This is our. This is TCP's, So from established, and after the connect, performing data and then, to the wave after this release process, from the three-way hand, after the three-way data transmission, and then, to the four-way release. This is the mechanism, a basic mechanism. Now, TCP, we just saw many, right? Yes. Port numbers actually range from, such a range. So, 0 to 1023. 0 to 1020, we call these well-known, that is, well-known, right? Now, these ports actually range from, such a range. Okay. So, 0 to 1020, we call these well-known. That is, well-known, yes. These are assigned to specific protocols. Right. You cannot use them, if you develop a no. You cannot misuse, you must apply to right? There is a set process, after the application, they will make a public, right? So everyone knows that this port number, right? Then they add it to their, right? Yes. Anyway. You can't just mess with, next. This port number. This port number. This port number. (1024 to 49,511). This range. The port numbers you can use them in a limited way. Actually, using them directly is usually fine. I mean, ports from 1024 to 65535. You can actually use, There's no major issue, There won't be any but some specific port numbers. You cannot use free, for example, something like 8080. Right? It's a backup port for our port 80. Yes, a backup. You can't just use ports like that randomly. Okay. So, during the communication process, it doesn't mean the port number is the same for both sides. Right? Here, we divide it into a source port and a destination port. So, what is a source port? It's when I initiate a connection. Whoever acts as the initiator. Their port is what we call the source port. If the other side is the responder, then its port is what we call the destination port. Okay. So, the source port on the initiator side, is randomly generated. Generally speaking, it's a random high port. A high port is a port number higher than 1024. So, greater than, starting from 1024. 1024 and above. What about the destination? It's a specific well-known port number. For example, you want to access the web application on this device. Like port 80. HTTP uses port 80, right? Or perhaps, HTTPS uses port 443. You want to telnet to this device. Then the destination is its port 23. Right? Any of these are It mainly depends on which port you want to access on the other side. It's like the example we gave before. You need to go to the cafeteria to get food, right? This window serves braised pork, right? The next window. It might serve seaweed egg soup. Maybe seaweed eggs, it's scrambled eggs with tomatoes, right? Each port number corresponds to a different window, corresponds to a different application. So you want to access the other side, right? When you, the student, run over there, you must find the right queue up at the right. You can't just run around randomly. If you run around you won't get the dish you want. It's the same principle. My source port number is a random high port. Then the destination is the well-known port number on the other side. The characteristic is your own is a random high port, and the other side is the destination port. Then on the return, this side is the initiator. Right? This side is the so how does it return? On return, its well-known port number. Port 23 replies to our port 1028. That's how returning packets work. It's always these two, because these two ports will eventually establish a TCP connection. They will establish a TCP connection. Understood? Ah. It doesn't mean it will reverse back completely, right? It won't reverse again. This port is now fully connected. This port is confirmed. As long as you bring up, this port is confirmed. Now, during this TCP phase, in the data transport layer, due to limitations of our intermediate medium, the data packets cannot be too large. They cannot be too large. They must conform to certain specifications. Right? Ah. Their size cannot be. Therefore, a very important action in the transport layer is segmentation and reassembly. Right? Segmentation means the large message, then reassembly, is putting the cut pieces back together. Right? Ah. Now, TCP and UDP they are different. TCP will cut it segment by segment for you, and then it will number them. It will number them for you. This is the first, this is the second, this is the third, then it sends them to the UDP, on the other hand, after cutting, does not number them. It sends them after cutting, it sends them directly. So, TCP in a complex network environment. For example, where there are many load balancing links. Right? Some packets may, right? Then, upon receiving them, the order might be received as 1-2-6-5-4-3, for example. Right? But that's fine. It has its own and can quickly reorder them. After reordering, it reassembles the data packet. Right? It just needs to reassemble the required data. This is quite simple, right? It's quite fast. But UDP is different. UDP sends directly. If the intermediate use load balance and some paths are then upon arrival, the order will be problematic. And when problems arise, your content might get altered. So, sometimes when we watch videos, the screen may become, the audio may be choppy. These are essentially some UDP issues. Okay. Here, each sequence number must be acknowledged. My first sequence number, right? The other side must confirm it has received that sequence number. Confirm what it has received, right? Both sides must acknowledged, right? If the other side does not acknowledge, what happens then? Without acknowledgement, it will request a retransmission. Suppose I have 6 packets, 1, 2, 3, 4, 5, 6. It already acknowledged 1, 2, 3, but then 6 didn't confirm, so what do? Let me send it to you again. It will retransmit. TCP will but UDP won't. UDP just sends it and forgets it. If it gets lost, it has nothing to do with me. So, UDP is a bit of a player, right? But don't assume UDP is weak just because of this unreliability. In fact, if we need to transfer large amounts of data, UDP is actually very efficient. If you use a web browser, you will see. When you download some files, you find the speed is very slow, right? But if you use some download manager software, right? And download via UDP, the speed could be even 100 times faster. Because the TCP process is just too cumbersome. Its efficiency isn't that high, right? As for UDP, its overhead is the overhead for our devices, the burden on the device is relatively small. Because it's connectionless. It also lacks retransmission and sequencing mechanisms. Or flow control it just tries its best to deliver, right? Okay. The protocols that use UDP are generally some, well, less critical ones. Or applications where I can just initiate it again. And the number of packets might be relatively small. These kinds of things like DNS, SMTP, SNM, and then DHCP and TFTP. And also our online, right? In online games, it just makes the character on screen warp a bit. Right? Just warps a few times. It doesn't really have, But reassembly is a different story. Just send it to the other, send 1, 2, 3, then it arrives out of order. This causes because it has no sequence numbers, right? No sequence number. Also, if a packet is lost, it's just lost. Lost is just lost, right? So for UDP, whatever arrives first, I just receive it, right? Then based on first come, first served order to arrange them. So actually, when using UDP, what's the best approach? The best approach is no load balanced links. Just take one path, right? Then what I send first, what I send later, the other side receives later. The order won't be right? Of course, packet loss can't be solved. Lost is just lost. And UDP is the same. It also has source and destination ports. Source port and destination port. On the initiators, its source port is also a random high port. The destination port, that is its well-known port. Okay. So what we just discussed is the content of the transport layer. Now, in the network, there is another major, we call it the IP protocol. As for the development of the IP protocol up to now, the main protocol versions we use are two. One is IPv4. The fourth version, its address, is 32 bits, and the other one is IPv6. This is the one we are currently pushing heavily. Right? It is 100. As for these details, we will cover them later when we get to IPv6 and elaborate on them specifically. About IP address, when we talk about we will explain them. The main function of the network layer is to take the packet from the source device to the destination device. Right? So both source and need a logical identifier. It is just like everyone. You have a phone number. Everyone needs a phone, right? Only in this way can I send this message, right? Only then can I read. Okay. The network layer, also called the this is in the TCP IP layers. Right? In here, IP is a very large protocol. Note the very first slide we showed at the beginning. The first page of our PPT. We call it the TCP IP protocol suite. Right? What does protocols in this use? One protocol contains many working protocols. It's a broad category, not a specific protocol. Of course, it is a protocol itself, but it covers many subprotocols. The main function at the network layer is to provide logical addresses for devices, known as IP addresses. In the early days of the Internet, we had other protocols used at the network layer that also provided logical addresses. For example, IPX. Older students might have used it. Back when when computers first entered China, right? This is a black internet cafe or small internet cafe. When we played Red Alert, right? Or Warcraft, we had to install IPX on the computers. Had to install the IPX protocol. Then, we could play on the, right? We could play on the, also, something like Apple's chat protocol, right? That's also a network layer protocol. These have gradually been phased out. You see anyone still using them? Right? Now, IP is the unified standard. All devices use the IP protocol. All use the IP protocol to provide this logical address for devices. It's like assigning a phone number to each device. To send a message, you dial the other party's number. And your call goes through. Right? The data content is then delivered. And it also provides packet routing and forwarding operations. How to get this packet forwarded through the intermediate links and devices. Right? This is what the network layer does. This is covered in the OSI model specifically. Now, the IP protocol. You need to understand its header structure. This header structure is quite complex. What we are seeing now is the IPv4 header structure. The IPv6 will be explained later when we study IPv6 in detail for you. The mainstream one is still IPv4. So, inside its size. Note that a standard IP header. The header of an IP packet ranges from 20 bytes to 60 bytes. Note, it's a range. Bytes. 8 bits. 8 bits equal 1 byte. Right? 1 byte. This is basic you should know this. You all know this. A standard IP can be as small as 20 bytes. And at its largest, it can reach 60. What does this depend on? It depends on whether options. Called options. Some optional whether any optional, if it is added, then it might need to if you add it. Then it might need to if you add it. Then it might need to if you add it. Then it might need to reach 60 bytes. Or if you don't have it, right. Then this is just 20 bytes directly. So the simplest header is 20 bytes. So the simplest right. So these 20 bytes include all these things, These are fixed at, Include all these things, This is 0 to 30, this is 0 to 30, this row here. This row here. One row is 4 bytes, what about here? So here. MO. Communicate. 5 rows. The one below this is the options field. Is some optional items. When you want to do some fancy tricks, you can use to add some option content. Some optional items. The add-on items are added in here. Right, okay, so in here. Let's go through them one by one. Go through them. What is the role of each bit here? What does it mean? Is its version marker? Version, for example, currently we have an IPv4 header. So this field indicates version 4. If it's IPv6, this field would be version. This field marks which version our IP header is. Next. What is the total header length? Hey, because our IP header has a variable length. So we need to confirm your header length. This uses 4 bits. Uses 4 bits to represent its header length. Then, TOS. TOS. What is TOS? What is it? TOS is used for IP data flows. To classify them. For classifying data flows. What is classification? For example, if some traffic is gaming, and this traffic is P2P downloads, and this traffic is video, we can shunt them. For your office traffic. I can prioritize it. Video streaming content. Well, I might, give it lower priority. Right? I can reorder traffic. This is something covered in the IE track. You'll learn about QoS. Quality of service. Simply put, it allows rate, it allows rate limiting. Then, total length. Here, it refers to the header length. Is this header 20, 60, 40, or something else? Right? So what does the total length field refer to? It includes the data part. Well, this data part comes from the transport layer. For example, content passed down, right? All of this is the data payload. Right? So adding this data part, plus the header, right, gives you the total length. It's represented by a 16-bit field here. It indicates the length of the entire packet. Okay, then there's an identification field. It identifies the packet, right? And a flags field. These fields are used relatively infrequently. They are used relatively infrequently. Then, the fragment offset. What does the fragment offset refer to? It refers to this part. After you fill in this part, your options might not be complete. For example, I want to add 11 bits. Right? I want to add, it's not a full 32 bits. What do we do? I need to offset it for you. That means padding with padded to a full 32 bits. This length will be padded for you. So there's an offset here. How many zeros did you pad at the end? It will be indicated right here. Its messages are all neatly structured. Here comes some basic computer knowledge again. That is, our memory. These messages will eventually be stored in our memory. Right? So, in the memory, what is its bandwidth? It's 8 bits. Each memory cell holds 8 bits. So when reading data, it reads 8 bits of data, ones and zeros. Right? It reads once. Stores, then another 8 bits. It stores another line. Then when the operating system reads it. For example, back in the Windows XP days, it was a 32-bit operating system. Although there were 64, generally we used the 32-bit one. Right? So, what does a 32-bit OS mean? How much data do I read from memory at a time? It's 32 bits. Which is 4 lines. It reads 4 lines from them. So here, as you can see, it reads exactly this entire line at once. It reads this entire row at once. For example, Windows 10. Most people install the 64-bit version. Right? So it can read 2 rows at once. Yeah. It can read 2, yeah. So its capacity, right? This is all extra knowledge beyond the curriculum. Moving on is TTL. We call it time to live. That's the survival time. The lifespan. This value. At the factory setting, when the packet is sent out, a value is assigned. Okay. Different device set this value differently. For our network devices, when they send it, the default is all ones, which is 255. Okay, 200. Some systems, like when it sends it out, it's 64. Okay, it is 6. Linux might be different. Right? Different operatings set different TTL values. No matter what it's set to. Every time it passes a router. Or passes through a network. Yeah. This TTL value decreases by, yeah. TTL is once it reaches 0. This IP header. This IP packet will be discarded. This packet will be discarded. So later on, we can use this TTL feature to do some operations. For example, probing our network to see what its path looks like. We can use this TTL behavior. Okay. Next is the protocol number. The protocol refers to what comes after its data portion. The next, right. What protocol is inside here? What the internal, so that later when we unpack it. During decapsulation, the corresponding protocol is called. To process it. To interpret it. Right, to interpret it. That's the protocol number. Next, header checksum. What does the header checksum do? It ensures the integrity of our packet during transmission. We say this packet travels over unreliable physical links. For right. So the packet might get corrupted after transmission. It might get corrupted. Inside, certain fields like these might become may change. It becomes, both are possible. Both, so, through a checksum. When I send this packet, a checksum value is calculated by a checksum algorithm. After the receiver gets it, also uses this checksum value. Also calculates the checksum value using this checksum algorithm. Then, compare it with the value here. Compare. If they are the same, I can confirm the packet I sent and the packet I received are the same and not corrupted. Right. If they are different, it means the data in between has been corrupted. This content will be dropped. And request the, if it is TCP, request the other side to resend it. Right. Then through IP, the bearer protocol. Send it to you again. Send it to you again. This is the role of the checksum, ensuring the integrity of our communication. Then next, our source IP and destination IP. Just like phone, as mentioned before. Right. Everyone has one. Each device will be assigned a logical address. The source IP address is who sends this packet. The destination IP address for this data is where it is going. Where to go. Right. It's like making a phone. This, the caller. This is the called party. Right? Just these two IP addresses. For IPv4, the length is exactly 30, right? Exactly one, exact, Then the options and data fields. I just roughly covered this. This is our IP header structure. The parts highlighted in red are more important, especially these one, These, TTL, protocol, then, source IP, destination, Later we can use this information to control the data. I can allow data packets to pass normally. Or block them. Allow it to, or block it. We'll cover access control tools later. You will learn this in the NA stage. Okay. So for this lesson, we'll probably stop here. What did we cover? We covered TCP's main mechanisms, as well as some of it, right? We didn't cover the head. Then for UDP, what are its message characteristics like? Right. What else? The IP packet. What does its header look like? That's what we covered in this lesson.